So welcome everybody, and thank you for joining this talk. Thank you very much. My name is Roberto, and I'm a software engineer in the ARM ecosystem. And this is the plan for the talk. First, I will go through two of the most important VR features, new VR features in Unity 5.6. Then I will show you the result of the Mali Graphics Debugger integration in Unity. I will perform a live demo, if I'm lucky. And then I will go through some of the mobile VR best practice that can help us to achieve, to improve the quality of our mobile VR applications with a low impact on the performance, which is really critical in mobile devices. And at the end, some thoughts about Vulkan in VR. So this time last year, in this very room, I shared in my last year talk our experience in porting to Gear VR our demo Ice Cave. And now that Daydream is now natively supported in Unity 5.6, I would like to share also our experience in porting our Ice Cave demo to Daydream. We all know that the plugin approach that we have been using for building Daydream's applications so far has some limitations. But thanks to the native integration of Daydream in Unity 5.6, those problems have been overcome. And now building Unity application for Daydream is simpler and easier. And above all, the application we built are now more efficient and performant because they are better integrated in the Unity rendering pipeline. So porting your application now to Daydream is as easy as ticking the virtual reality supported option. Then we need to add the Daydream VR SDK to the list of the SDK our application supports. For Daydream, we need to set as a minimum API level Android Nougat. And that's all. We are ready to go. We build our application. And I have to say that the first time I followed those steps, I got my application working perfectly in the first attempt. So it is really easy now to build a Unity application for Daydream. Just a few words about the list of the VR SDK. Our application can be built with support for several VR SDKs. I tested, for example, with the Oculus and Daydream. It is important to notice that the device will be initialized in the same order they appear in the list. So, for example, if building with this setup, I built for Android as a Daydream, as I said, and I got very similar results on Daydream device and Gear VR devices. So building with this setup, it means that the devices, the Gear VR devices will go first through the Oculus SDK, and other devices will follow to Daydream. Unity 5.6, the Daydream controller is not yet integrated, so we need to keep the Gear VR SDK in our project, and then we need to add to our scene only the controller, only the event system and controller main. That will allow us to access the controller methods to check for the buttons, the interaction of the user with the different buttons. So it's not completely yet integrated, but it's just the controller that left to finish there. We hope that in the next version, or patches for the 5.6, this Daydream controller will be fully integrated in Unity as the mouse pad in Gear VR. So the second most important VR feature implemented in Unity 5.6. It is a single pass stereo rendering. We call that in mobile multi-view because this is the name of the extension that allows to implement the single-pass stereo rendering. If we look at the pipeline and the traditional pipeline for the stereo rendering, we see there that for rendering the same image, the same scene, we need to issue 2 draw calls, 1 draw call per eye. So here is where the multi-view extension comes to the rescue. The multi-view extension allows to render the same scene from different point of view with a single draw call. So now our vertex shader, in the case of a single pass or multi-view, will look something like that. We will use an array of transformation matrices, and the vertex shader will be executed only once, but that line, which is in red, will be executed n times. In Unity, for single pass stereo rendering, we use only two views, but there are other cases where we can use more views, for example, when implementing forbidden rendering. I won't talk today about this feature. It's not implemented in Unity yet. Here you can see, for example, the CPU-GPU timeline for an application which is almost CPU bound. So the CPU spends some time rendering the left eye, the right eye, and then in composing the side-by-side image, final image that we see in the headset. And the same, there is also some load on the vertex processing and fragment processing. If we compare this CPU-GPU timeline with the timeline when we use single-pass stereo rendering, we can see that the load on the CPU has been reduced by half. So it is really important if our application is CPU-bound to use single-pass stereo rendering, because we will drastically reduce the load on the CPU. We will also benefit from some reduction of the load on the vertex processing, but on the fragment processing on the GPU side, there won't be any changes, as we are rendering, finally, we are rendering the same amount of pixels independently of the approach, multi-pass or single-pass. We performed in our team at ARM some research on the CPU load and vertex load when using the single-pass approach or the multi-view approach. And what we saw is that when incrementing the number of draw calls, we see a reduction on the CPU load. Our test scene was composed by many cubes, and for rendering each cube, we issue a single draw call. So when we are issuing around 100,000 or near 1,000 draw calls, the reduction on the CPU load is almost 50% in comparison with the load we will have when rendering with a multipass. The same, we could see the same trend when researching the load on the vertex processing. So the higher the number of draw calls we issue, the more reduction we got on the vertex processing in the GPU side. And here I'm showing the output. This is a screenshot from the Mali Graphics Debugger on the Icecave VR demo, built with multipass and with a single pass options. And you can see in the below figure that the number of vertices, draw calls, and indices are almost half of the figures in the multipass rendering approach. Last year, I also showed how to implement stereo reflection in Unity. For that, I showed how to synchronize the main camera with two additional auxiliary cameras that were rendering reflections from each eye. But now, in Unity, we got access to a new built-in uniform, which is the stereo eye index. So we can, in our vertex and fragment shader, we can use this new built-in uniform to query about which is the eye which is rendering and take the decision to, for example, use one texture or another. The result, you can see the result in this picture where we use that new built-in uniform to render the stereo reflections in the central platform of the ice cave. It is in the ice cave demo, where we are combining reflections of the Phoenix, which is the dynamic object there. We rendered those reflections with two different cameras at runtime, rendered into a texture, and then we combined that those reflections with reflections built using a local cube map. We used for static reflections the local cube map technique, and we use a single cube map, but two different reflections vectors. So we now can query that new uniform to decide which vector to use and which texture to use. And now it is really easy to implement stereo reflections. So the message here is very clear. Enable single-pass stereo rendering in Unity, especially if your application is CPU bound. But in general, you will get, as a benefit, a reduction on the CPU load and some reduction on the vertex processing. Let's talk now about Mali Graphics Debugger. For those which are not familiar with Mali Graphics Debugger, just a few words. This is a graphic debugger which is capable of tracing all API calls from frame to frame and inspect all the objects that are used in every call. MGD can trace application that has been built using OpenGL, VR and non-VR, Vulkan, non-VR of course, and OpenGL. So MGD is available for free from the ARM developer.com, and also with some license you can debug other non-Mali GPUs. But the most important is that it is for free to debug our Unity applications running on ARM Mali GPUs. So thanks to the collaboration with Unity, I'm glad to announce today that Unity 5.6 can build Android applications with full support for Mali Graphics Debugger. And now it is really easy to use Mali Graphics Debugger to debug Unity applications. For that, all you need to do is first to place the MGD library provided with the installer in your plugin Android folder. Then you need to tick the development build option in the build options. You build your APK, you deploy your APK, and you connect your Android MGD application over USB, and you are ready to go and trace your applications. I will show you now a live demo on it. But just to mention that for Vulkan, the process is very similar, and just with a few steps, you can you can build your applications in Unity using Vulkan with the full support for MGD. Let's see now how it works. So I got here already Unity. This is the Ice Cave project. And I got here in the asset plugin Android, I have added the libmgd, which is provided with the MGD installer, with the application installer. I build my project and click here. I set the development build option. This will allow Unity to package the library into the APK. So the next step is to install the application. I have already installed it. I have already installed it. And I've got here in my device the MTD Android application and my, of course, my APK from the Ice Cave build with support for MTD. What I need to do is first to launch, you won't see there, but to launch the MTD Android application, you need to slide a button to the right to enable it, and you will see a list of all the applications of the APK installed in the device that contain the MTD library. So the next step is to connect, using this command to connect the MTD, Android MTD over USB. So, okay, now we launch the MTD application, the desktop application. We click over this is the connect button, the connect to the target. And now the application is just waiting for traces. We haven't launched yet our Ice Cave VR. So we launch, but from the list of the application listed by the MTD debugger. So we will launch Ice Cave VR. And now the MTD debugger starts to receive the traces. It takes a little time. Now appear, okay, now we are there, and it's registering all the frames of the application. So I will stop at this point, and we can see here all the frames, and we can go from frame to frame and inspect any of the draw call, look, search for any API call. GL bind texture. It will show you all the EGL bind, for example, GL bind texture. So you can search there for any command, and then you can inspect any command and go. You can inspect any object there. For example, buffers, texture, everything. So I won't go into detail. You can find in the armdeveloper.com. You can download for free the MTD, and there is a very nice tutorial. I really encourage you to use it because now it is really easy to use once it has been integrated in Unity. So let's continue. So also you can save all your traces for later inspection, so you don't have to go through all this at the runtime. So I won't do it. I will close my application. We'll close this. I will close Unity as well. Okay. So let's continue with the slide deck. So now I would like to go through a few best practices that could help us to improve the quality of our mobile VR applications at low cost, at really low cost, which is really important in mobile devices. First of all, anti-aliasing. So in mobile VR, we see the final image, so very close to our eyes, so any aliasing, any artifact will be magnified. So we strongly recommend to enable 4-time multi-sampling anti-aliasing in Unity, as it is practically virtually for free for ARM Mali GPUs. So the impact on the performance is really, really negligible in ARM Mali GPUs. We can make use of these advantages. Secondly, we strongly recommend to use ASTC text to compression. Why? Because ASTC text to compression allows a wide range of options for compression. So we can wisely decide where to use less compression because a given asset needs a high visual quality, or we can decide where to use higher compression where a given asset doesn't need high visual quality because it will be rendered far away from the camera always. Additionally, ASTC supports other texture formats as 3D texture. And finally, and the most important, ASTC is available on all Daydream and Gear VR devices. So don't ignore that compression format. It is the best format available for texture compression. And finally, now I would like to go through a few highly optimized rendering techniques for mobile and for mobile VR we have developed in-house to achieve high quality rendering in mobile devices at low cost, at very low cost, with saving runtime resources, which is critically in mobile devices. So I'm talking here about several rendering techniques based on local cubemaps we have developed in-house. They are listed in this table. I'm talking about shadows based on local cubemaps, reflections based on local cubemaps, and refractions based on local cubemaps. All these techniques have in common that they are based on local cubemap. So they are based first, we render a cubemap offline, we render some feature of the scene. I will explain you now with the example of the shadows. And then at runtime, we apply a local correction to a given vector depending on the technique, and we use that vector to fetch the texture from the cubemap and render shadows, reflections, or refraction. For example, in the case of the shadows, when rendering the static cubemap line, we render the transparency of the boundaries of the scene in such a way that, for example, if that door is open, we place our cubemap in the center. We render the cubemap from the center of the volume of this volume, and when rendering the scene in the cubemap, if we are rendering an opaque geometry, we write in the alpha channel of that pixel 1. But if we are rendering the door where there is no geometry because the door is open, so there is no geometry, or if the geometry is completely transparent, then we render in that pixel 0 in the alpha channel. And then at runtime, we do the following procedure. For the case of shadows, I won't go into detail for reflections and refraction. You can find all this detailed information in the links I will provide at the end of the talk. So in the case of shadows, we first, in the vertex shader, we build the vector from the vertex to the light. And we pass that vector as a varying to the fragment shader in such a way that we get in the fragment shader interpolated the vector from the fragment to the light. And then we find the intersection of that vector with the proxy geometry. We use as a proxy geometry the bounding box, which is the simplest proxy geometry we can use in this case. So we find the intersection of the fragment to light vector with the bounding box, and we build a new vector from the position where the cubemap was rendered to that intersection point. We call that process local correction. And then we use the local corrected vector to fetch the texture from the cubemap we previously have rendered offline. If when fetching the texture from the cubemap, we look at the alpha channel, at the value of the alpha channel, if we look there and we got 1, it means that in the direction of the fragment to light vector, we got a fully opaque geometry. So what it means that the light can't reach that fragment, and that fragment is in shadows. If when fetching the texture and looking to the value of the alpha channel in that fragment, we read 0, it means that in the direction of the fragment to light vector, there is no geometry, or the geometry is completely transparent. It means that the light can reach, the light coming from the light source can reach that fragment, and that fragment will be fully lit. So in practice, when we render the cubemap offline, we build a map of the zones where the light can come through the can come through from the boundaries of the geometry and can reach the scene. That you can find a detailed information on how to implement this technique. It is available in the Unity Asset Store. You can download the project. There is a full project and fully documented. You just copy and paste the shader into your project. And this is how it works in this small demo. So we can see there a change in the position of the light source, and the shadows are automatically updated. And we can see also a nice effect, soft shadows. We can control the softness of the shadows by interpolating the cubemap min-maps. So we build offline, we render offline not only the cubemap, but also all the possible cubemap min-maps. Sorry. We need that to implement the soft shadows effect. And this is how it looks, the reflections based on local cubemaps. Here we are combining two types of reflections. Reflections coming from the static geometry, all the geometry of the room, which are rendered using the local cubemap techniques, and those reflections as well. And reflections based on reflection from the dynamic object, which are the chess pieces, which are rendering using a mirror camera, which is rendered every frame to a texture, and we are using that texture and combining that texture with the texture coming from the cubemap to have a full picture of reflections there. And here, I'm showing a picture I took in the Taiwan airport when I was going to the gate. Why? Because I was going with my partner, Sylvester, and I told him, oh, this is a special, I mean, the best use case for using reflections based on local cubemaps. You can see the reflection of all these symbols in the wall on the corridor. And you can see that the reflections, they are blurred the farther away they are from the light source, which is on the wall. And we can implement that. I implemented that just the next day I arrived home. So this is, look at the reflections of the window on the chessboard. And you can see there that the reflections of the window, they are blurred the farther away they are from the wall. Look carefully. So why we recommend to use all these techniques? First, because they are faster than other traditional techniques that render to texture every frame. They are faster. I measured that in this interval. This interval is valid for shadow, reflection, and reflections. Secondly, and it is really important, they use less bandwidth. Why? Because they perform only reading operation from the cubemap. The cubemap was rendered offline, and at runtime we just perform reading operation every time. If we compare with shadow mapping technique, where we render the shadows every frame to a texture, we write the text to the texture, and then we read from the texture. So in this case, we are halving the use of the bandwidth, which is a critical resource on mobile devices. An additional advantage is the quality. These techniques offer better quality in shadows, in reflections, in refraction. Why? Because every frame we are fetching the texture from the same cubemap. While if you look carefully, for example, for reflections based reflection implemented using a mirror camera that render to texture every frame, they are rendering to a different texture every frame. So even if we don't move the camera, we will see in the image some pixel flickering or pixel instability because the texture is not the same. And lastly, these techniques allow implementing those nice effects such as soft shadows or blur reflections. So use this technique when possible. They have some restriction, of course. Use this technique when possible, and when combining with other traditional rendering techniques, they help us to achieve better quality at very low cost. So now, final words about what next in VR. The big next is Vulkan, of course. When it will be available, I don't know. This is a question I always ask. I'm just crazy waiting for it. In this picture, I'm summarizing the benefits of Vulkan in non-VR applications. So if we compare Vulkan versus OpenGL, the main difference there is that several responsibilities that were before in hands of the driver have been moved to the application level. And the advantages of this shift are really important for mobile. It means lower CPU load, less CPU load on the CPU, and higher memory of on-chip, higher usage of on-chip memory that ultimately leads to less energy consumption and longer battery life, which is really important for mobile. I will show you now, let me just go, short video that summarizes our research, a research work we did in collaboration with Infinite Dreams. I got some sound there. I can't hear the sound. Okay. So in collaboration with Infinite Dreams, it is the studio that developed the Skyfall Reloaded mobile game. In collaboration with them, we measured the energy consumption on the SoC for the game built on Vulkan, built with Vulkan and with OpenGL. And as you can see there, what we found is that there is a less energy consumption in the range of 10 to 12% when the application is running with Vulkan. So we can expect similar benefits from Vulkan in VR. It's just logical. So let's wrap up. Let's do a quick wrap up with the main takeaways. First of all, update to Unity 0.5 if you haven't done yet. Why? Because you will benefit from the native support of Daydream and Google Cardboard if you're building your application for those platforms. You will benefit from MTD integration in Unity. Now using MTD will be easier and faster. And you will benefit from the single pass stereo rendering that will help you with lower load on the CPU and the better processing. As part of the recommendation to improve the quality of our VR applications, we strongly recommend to enable multi-sampling, anti-aliasing, to use ASTC texture compressions, and to use mobile-friendly rendering techniques as those I have shown. And finally, we can expect from Vulkan performance and energy consumption improvement as we already seen in non-VR applications. With this, I finish the talk. I'm ready for questions, if any, and I leave you with this last slide where I'm pointing here to several links where you can find in detail information about all topics that I have been talking today. So if there is any question, please come to the mic, as I was recommended to ask by the support team. Thank you very much for attending the talk, and thank you very much for listening to me. Thank you.